right? So the final feedback system is implemented by this function, right? By this piece of code right here. And this function, for this we have used input capture mode of the timer, in which we are basically determining the frequency of the detected frequency of the motor, and corresponding to that we are measuring the speed. In order to do that, we use this callback routine for the input capture, and we determine the time duration between two successive rising edge. And based on those two successive rising edge, the duration between those two successive rising edge, we can calculate the frequency as well as the measured speed. So essentially, this is simply the conversion from radian per second to RPM. And since we have a 10 kilohertz timer, as I discussed previously, we can calculate the frequency using this formula here. Both the measured frequency as well as the speed is then displayed on the UART right here on the PuTTY terminal, which is done using the UART configuration that we did earlier. After that, we have um, basically the ADC read function here right here, which is done by using the potentiometer. This potentiometer right here, depending upon what the value of the potentiometer is, this is read using this particular command of hardware abstraction layer ADC get value. Since we are using ADC1 to read the value of the potentiometer, we get that value, and then we determine the required reference speed. Since we want the reference speed to be between 0 and 60 hertz, compare in map from the duty cycle of 0 to 1, we simply determine or claim the edges for here right here. Other than that, this is pretty much straightforward and same as before. This particular part here is the implemented PID with the canonical form, and where we basically store the previous commands, and as well as the previous errors in order to calculate the new command for the PID. This is done using this non-canonical direct form. You can read the theory for this, but essentially this is what it looks like in the analytical form. Based on based on this, the PID code is a PID command is generated and is fed uh, into the motor driver. Other than that, I wanted to discuss this particular part right here. So essentially, in order to calculate the PID gains, we have this PID, this feedback system simulation in the MATLAB, where you can clearly see we have the reference input, we have the PID block that we have used automatically given by the MATLAB. Then we have the saturation block right here in order to deal with the with the wind up, and then we have the anti wind up controller as well, which having the gain of kW, and we simply convert it uh, into the analog with zero order hold, and finally we have the plant GC, which is given in the MATLAB right here. For that, this is transfer function of the motor itself, and these parameters are taken from the datasheet of the um, motor itself, right? So if I run this, I already have run this, so to cut short on time, and these are the outputs that we have. So as you can clearly see in the open loop response, it takes quite a while in order to settle down to the desired speed, but if we look at the closed loop response, we can observe the overshoot here right here, but a much reduced settling time compared to the open loop response. And these are with the control inputs, and as you can see that uh, as soon as we introduce the PID controller, the output basically follows the input exactly, right? Right, so this is pretty much it. I will share the code file for this feedback flow system of the motor control with the digital PID controller implemented on Nucleo F401 board, so that you can implement it yourself. And yeah, I'll see you in the next video. Thank you for watching.